25B notes. And we're going to use some of that information that we had talked about Friday before the quiz. So if you'll just kind of like flip back real quick and look at your Friday notes, we talked about the linear factorization theorem that said a polynomial would have the same number of zeros as it does its degree and would therefore have that many linear factors. So if it's an nth degree polynomial, it has n zeros and n linear factors. And then we did the problems where we wrote the polynomial given some zeros, and we had kind of added that little piece. If there's a complex zero, we know there are actually two zeros there, so we can name another zero. So our first example is kind of building right off of that idea from Friday. So we want to use the given zero to find all the zeros. Now after this slide, I'm going to take away all my hints. Right? So like now you still have a hint because I'm giving you a zero. Just like back in section 2.3 I would say verify x plus 2 is a factor. So it's giving you a hint. Eventually I'm going to take that away. So we've got f of x equals x cubed plus 4x squared plus 14x plus 20. We've got a 0, a negative 1 minus 3i. How many zeros should we end with here? 3, because the degree of the polynomial is 3. So I gave you 1, and then instantly you know the conjugate is also a 0. So if negative 1 minus 3i is a 0, what is another 0? Negative 1 plus 3i. Okay, so now I have 2 of 3 zeros. Let's work out a plan here. How might we be able to find our missing 0?
Multiply those two zeros together and divide the bigger polynomial by that polynomial.
Okay, so write those as factors.
Yeah.
Write out your linear factors for negative 1 minus 3i and negative 1 plus 3i. Multiply them together. What type of polynomial are you going to get? If you multiply two linear factors, thank you, Nick, you're going to get a quadratic polynomial. And then if we take our cubic polynomial and divide it by a quadratic polynomial, we're going to be left with a linear factor that must be the other 0. Okay, so we're going to use our polynomial division. So let's go ahead and do like Jacob says. We're going to write these out as zeros, or linear factors, I should say. Now I'm going to show a little bit more work. Some people may skip this step, but I'm going to show x minus the quantity, negative 1 minus 3i, and x minus the quantity, negative 1 plus 3i, which could then be written as x plus 1 plus 3i and x plus 1 minus 3i. So some people will skip that first step where they write the complex 0 in parentheses. They could just distribute the negative to both terms. I'm okay with that as long as you can be careful with signs. If you're going to have an issue with your signs, then you ought to write it down and distribute the negative. So you decide what works best for you. This is that point where you could multiply trinomial by trinomial, but I'm not going to do that. I'm going to use my shortcut, recognizing that these are going to end up being conjugate binomials. If I regroup, x plus 1 and x plus 1 are the same, so that could be my a term. And then we could think about this like a complex value, right? So we could say a plus bi and a minus bi.
Is this the only way you can do it?
You could do it as a plus b, a minus b, or you could multiply trinomial by trinomial. Those two things make sense to you? Okay, so give me 1 second, okay, and then I'll show you another way to do it. If we multiply two conjugates, what do we know to be true if they're complex? It will turn out to be a squared plus b squared. If you multiply two complex conjugates together, we wrote this down in our notes, back in complex numbers 2, 4. If you multiply a plus b times a plus bi times a minus bi, it will always, we did the work once, it will always come out to a squared plus b squared. So if you can identify an a and a b, then you can just sub those things in. So what's my a? X plus 1, and then I gotta square it. What's my b value? 3. So it would be plus 3 squared. Then I just have to multiply out x plus 1 times x plus 1. That's x squared plus 2x plus 1 plus the 3 squared, which is 9. So that quadratic that Nick said we would get is x squared plus 2x plus 10. If I did quadratic formula with this quadratic, my solutions would be -1 plus or minus 3i. So we're undoing that. Now, in response to, like, Isabel, she's not really jiving with that method. So we had x plus 1 plus 3i and x plus 1 minus 3i. If you are more comfortable, you could do from here distribution. So you could do x squared plus x minus 3ix. And then you'll multiply the 1 by everything. So you'll get plus x plus 1 minus 3i. And then you'll multiply the 3i by everything. So you'll get plus 3ix plus 3i and then minus 9i squared. But see, for me, that's just a lot of terms to keep track of. But when you combine this, let's see, we're going to get x squared plus 2x. These cancel out. I got plus 1. These cancel out. And -9 times I squared is plus 9. So it's the same thing. Any other questions about that multiplication that I did there? Okay, so remember back to our plan that Jacob had given us. If we find that quadratic for those two imaginary zeros, then when we divide this cubic polynomial by the quadratic, if they're both zeros, we should still end up with a remainder of 0, and we'll have our missing factor. So now I'm going to do long division. X cubed plus 4x squared plus 14x plus 20 divided by x squared plus 2x plus 10. Okay. Remember, keep long division with polynomials simple. Don't make it really, really hard. You can only focus on a few things. So you're going to start with the first terms. X cubed divided by x squared is x. So I'm going to put that above the x term over there. I'm going to now distribute it to every term in the divisor. So I'll get x cubed plus 2x squared plus 10x. Then I know in long division from 3rd or 4th grade, I would normally be subtracting this line here in red. Since it's made up of many terms, I have to subtract every term, so they're all going to change signs. So this is going to be minus, 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 since they're all positives. Do the work, I'll get 2x squared plus 4x, and then bring down my 20. And repeat your process, right? Don't worry about everything. Just worry about the first terms. So I've got 2x squared divided by x squared. Leaves me with a plus 2. Multiply that 2 by everything, and what do you notice? When you subtract this, you're going to get a remainder of 0. That's because you're dividing by the quadratic that is made up of the two other zeros, so they would give you remainder 0. Okay, so their product gives us remainder 0, which means the extra factor is x plus 2. So there's our missing factor. And that could be our extra 0. So our extra 0 is -2. So find all the zeros, given the 1 0 that I know. The first one was fast. Second one, I had to do a little bit more work. All right, questions, concerns? Okay, now the next 2 slides, we're going to be writing down a lot of stuff. And so I'll give you time to write, but make sure you're like on task writing, so that we can talk about it. We'll do the 2 slides, and then we'll do an example putting those things to use. Okay? So the first thing we want to talk about is the rational 0 test. If you're following along from your Algebra 2 notebooks, in Algebra 2 this is referred to as the rational root theorem. So in the beginning, there's just like a quick stipulation, right? The polynomial has to have integer coefficients, so nice number coefficients. Most of our polynomials that we work with are going to have integer coefficients. Then it talks about every rational 0 of f has the form plus or minus p over q. So you don't have to worry about whether it's positive or negative. It could be either. Because we could use positive factors or negative factors to get our P's and our Q's. But I want to talk about this word that's in the name of the test as well, the word rational. So think about the word rational. It's a subset of the real numbers. Every real number can be placed either into the rational or irrational category. Have a quick chat with the people at your tables. Do you remember what rational numbers are? Or irrational numbers? Sometimes working the opposite is better.
Irrational study.
So, irrational.
thinking that these 2 seconds is
No,
not
I
true.
was gonna say.
Okay, let's come together and see what kinds of things we chatted about. What were some things if you thought your group had a good definition of rational? No groups were able to define that nicely? Were you able to give me examples of rational numbers? Whole numbers are a subset of the rational numbers, sure, so 0, 1, 2, 3, so on are rational. Can you give me any examples of irrational numbers? Pi. Why is pi irrational? Keeps going. So that means that rational numbers would end or terminate. What else is weird about pi? Besides the fact that it keeps going. It never repeats itself. It never goes into a pattern. So there are some numbers like 0.3 repeating. That never ends, but that is considered rational. What is 0.3 repeating? 1/3. Okay, so that's considered a rational number. What math word is in the word rational? Ratio. And what do ratios look like in math? Fractions. So if I were going to put in a nice definition for rational numbers, I would say rational numbers are numbers that can be written as fractions. Now, in decimal form, they're either decimals that terminate or decimals that repeat themselves. And then decimals that don't do those things are considered irrational, like pi or the square root of 2 or the square root of 3. Those things are irrational. They don't come out nicely. Okay? So this test will only help us find rational zeros. We may be able to, after the test, we may be able to find complex, like imaginary zeros, or some irrational conjugate pairs, like 1 plus or minus the square root of 3. But using this test, you're only going to be able to find ones that could be written as fractions. Okay? And P and Q have to have no common factors other than 1. So the P over Q, you wouldn't see like 6 over 4. You would reduce that to 3 over 2. It's just a reduced fraction. And P is the factor of the constant term. Where do you normally see constant terms in polynomials? At the end. You can put factors of the constant term over factors of the leading coefficient. Where do you normally see the leading coefficient? In the front. So we do like the P's and the Q's on the front and the back of the polynomial, and then we make the fractions. Okay. Good. We'll do that in our example. But first, we want to also write down Descartes' rule of signs. So this should also be a little trip down memory lane. In a little bit, I'll move it up because I know when it's down at the bottom, it's hard for people at the bottom. So jot some things down, and then I'm going to move it up. But you can't read the rest of it.
Goal. Identify the positive number and type of zeros. Rule of signs. Let f of x have real coefficients.
You need a magnifying glass. That's what I'll get you for Christmas.
Oh, Tristan's
Like 3, I think. 1 page per year.
water damage or not?
Smudge. How does it not even smudge? You ever just like put your thumb on it and then you're like, no. All done. What size lead do you use?
0.5.
Dude.
No, I use 0.7 as my other pencil I lost.
27. That's pretty big for that small.
I'm
Right?
sorry. I'll move down.
You can use whatever you want. Notice as you're writing the rules for positive and negative that you have 2 different function notations, so you'll have to pay attention to that. Okay, so some qualifications to use Descartes' rule of signs. This time, your polynomial has to at least have real coefficients, not necessarily integer coefficients like it would for the rational root theorem. And the constant term cannot be equal to 0. If there is a constant term that's equal to 0, if the constant term is equal to 0, then you don't have a constant, and everything else has an x. I'll show you this in my example next. But then you could factor out the x, and you can still do rational zero test and Descartes' rule of signs. So know that you might employ factoring with these other methods as well to make it work out. But I'm going to look at the example f of x equals x to the fourth plus x cubed plus 3x squared minus 1. Now, all that Descartes' rule of signs does for us is it narrows down what is possible for us. So when we're doing the rational zero test and we're checking the plus or minus p's over q's, if we have done Descartes' rule of signs and we find out that there are no sign changes for f of x, which would mean there are no positive zeros, then we don't waste time checking positive zeros. So Descartes' rule of signs, you really want to think about it as a method to work smarter, not harder. Sometimes Descartes' rule of signs doesn't really narrow anything down for you, so then it's still up in the air what you decide to test with the rational zero test. So positive zeros, I'm going to work this out as I kind of go through it. Count the number of variations in the signs of f of x. So from term to term, how many times does the sign change? Well, x to the fourth is positive, x cubed is positive, x squared term is positive, and then finally my constant changes to a negative. So there's one sign change. That means that there is equal to or less than that number by an even integer. What is an even integer? Give me an example. 2. You could also do 4, 6, so on and so on. So 1 minus 2 would be negative 1, and it wouldn't make sense for there to be negative 1 positive real zeros. It's either 1 or none. So, and none is not an option because it's not less than that by an even number. So I now know there is one positive zero. There absolutely has to be one positive real zero for that function. For the next one, the negatives, count the number of variations in the signs of f of negative x. So you'll remember doing f of negative x back in chapter 1 when you were doing even and odd tests. Know that you're not testing for even odd functions, so you don't have to prove this. I don't need to see all of your work. So I'm just going to figure it out. If I plug in negative x to an even exponent, then my term stays the same sign, right? So this is going to be positive x to the fourth. If I plug it into an odd exponent, then my term is going to change signs. So this is going to be minus x cubed. This is even, so it's going to be positive 3x squared. And then there is no x, so it's going to stay negative 1. Now count the sign changes in f of negative x. So it was positive to negative is 1, negative to positive is 2, and positive to negative is 3. So for the number of negative real zeros, there is either 3 or less than that by an even number. 3 minus 2, 1. Negative 0. So when you're listing these 3 or 1, it's going to be 3 or 1, 2 or 0, 4, 2 or 0, 5, 3 or 1. Right? It's going to go down by an even integer by 2 each time. But it's not going to be 1 or 0 because there's not a difference of 2 in between those. Okay? So on this one, what I can tell is there's definitely a positive real zero. Maybe I have one negative real zero, and then my other 2 zeros are imaginary. Or maybe I have one positive and 3 real negative zeros and no imaginary solutions. But because this was degree 4, I have to have 4 zeros. So let's do an example where we kind of put all of this stuff together. And we're going to do two things at the end. We're going to write it as a product of linear factors, and we're also going to list all the zeros. I usually do those in the reverse order. I find all the zeros, then I write the factors. And we're going to work with f of x equals 2x to the fourth plus 3x cubed minus 8x squared plus 3x. Okay, so this is the type of problem I'm talking about when I say I take away all my hints. I just give you a polynomial. I don't tell you to verify anything, so you don't know where to start synthetic division. And I'm not giving you one complex zero, so you know another complex zero, and you can find their quadratic factor. I'm just saying, here's polynomial, give me all the zeros. Now, you can always check a polynomial at the very beginning to see if you could factor it. Because if you could factor the polynomial, like factor by grouping or some other method of factoring, then you wouldn't have to do all the like synthetic guess and check, rational zero test, stuff like that. What do you notice about all four terms in this polynomial? They all have x. So really on this problem, you probably need to factor out the x first. If you think about your plus or minus p over q, that's not a very exciting test if the constant is 0. Then its only factor is 0. Okay. So what you probably want to do here is factor out the x first. So we'll get 2x cubed plus 3x squared minus 8x plus 3. And that factor of x means that I have a 0 at x equals 0. Okay. So if I'm listing out my zeros, I have 1 to list. The other zeros I still got to find. I might look at the cubic polynomial inside those parentheses and check if I could factor by grouping. But if I take out the greatest common factors, my 2x plus 3 and 8x minus 3 are not going to be the same. So I'm not going to factor by grouping. So now I'm left with rational zero tests. So first thing I'm going to do is list the possible zeros. These are possible rational zeros that I'm listing here. These are your plus or minus p's over q's. I'm doing more work because these are your notes, so I'm writing that out. So then we look back, and we're just going to look at this cubic polynomial where our constant is no longer 0. The factors of your constant are your p's. So what are factors of 3? 1 and 3. And then the factors of your leading coefficient, those are your q's. What are your factors of your leading coefficient? 1 and 2. And you don't have to worry about positive or negative, like if that was -2, don't worry about it because in front of everything you're going to put a plus or minus, right? So signs are irrelevant here. So we're going to say plus or minus for our list. And then we're going to take the p's, 1 and 3, and put them individually over each q. So I'm going to first take 1 and 3 and put them over 1. Well, that would be 1 over 1 and 3 over 1, which is 1 and 3. And then I go back and I take my p's again, 1 and 3, and I'm going to put them over my other factor of my leading coefficient, which is 2. If it reduces to be a number that's already on my list, I don't write it twice. But if it reduces and makes a new value, then I'll put it on my list. So 1 over 2 is new, and 3 over 2 is new. So those are my possible rational zeros. If a rational zero exists, it has to be one of those numbers. How many zeros do I have there? 8. 4 positive and 4 negative. Now, here's where Descartes' rule of signs come in. If I do a quick check for Descartes' rule of signs, I might be able to say there are no positive zeros, so don't check positives. Or there are no negative zeros, so don't check the negative zero numbers. So I'm going to do Descartes' rule of signs. I'm going to call it DROS. If you need to write that down, that's Descartes' rule of signs. And I'm going to check for the positive, and then I'm going to check for the negative. So what are the possible numbers of positive real zeros and negative real zeros? Okay, if I'm checking the positives, I'm going to go back up here to my f of x where I factored out the x, and I'm just going to look from term to term in the cubic polynomial, how many times did my sign change. So it's positive, positive, negative. So there's one sign change, and then negative to positive is 2. So there's either 2 or 0. Okay. So in this list, we had 8 possible zeros. 4 of them were positive. It's possible that 2 of them work. It's possible that 0 of them work. Okay, so I could take a chance on that. For Descartes' negative real zeros, I'm going to write down what my f of negative x is and see if there are any negative real zeros. So f of negative x, I'm just going to use the cubic one. So that's going to be negative 2x cubed. This will be plus 3x squared. This will be plus 8x, and then plus 3 will stay the same. I just go through, and any that are odd are going to change signs. Any that are even are going to stay the same as what they were before. How many sign changes do you have here? Just the one. Okay, so this is a good example where I've done Descartes' rule of signs, and my list of possible rational zeros is quite small. So I'm going to say, like, this is a toss-up. If you want to try the positives, it's possible that half of them work and the other 2 don't. So you might find a 0 real fast. Or if you just want to be like, I don't know if there's even going to be a positive 0, but I know there's definitely going to be a negative 0, then you could try the negatives. Okay. But I think on this one, people could argue for either way. So let's set up synthetic. You try a 0 from the list. And someone let me know if they find one that works. What are we looking for? At the end. Zeros. Pick a number from that list of possible rational zeros. Do you want to pick a positive? Do you want to risk it? Do you want to pick a negative? Because you know there is one. It's totally up to you. So you can pick 1.
Negative
3. 1 half. 3 halves. Carter, you found negative 3?
Yeah.
Okay. So I'm going to put negative 3 on the outside of mine. Maybe you tried negative 1 first, and it didn't work. So then we'll put negative 3 outside, add down to get 2, multiply for negative 6, add down for negative 3, multiply to get positive 9, add down to get 1. Oh yeah, this is great. I'm happy. Found a 0. So up at the very top I had a list of zeros. I can now add negative 3 to that list. At this point, you have options. You could keep trying synthetic. Now that you found the one negative, you could go in and check some of the positives. Did anybody find a positive? Did anybody test a positive? You found 1 and then 1 half. 1 and 1 half. Okay, so 1 works and then 1 half also works. So you could do that, but I'm going to illustrate what I would normally do. If I do synthetic, and remember, we were doing this with a cubic polynomial right here. And I get it down to something that is quadratic. I don't keep guessing checking. If it's quadratic, 2x squared minus 3x plus 1, I can always solve that, whether it's by factoring or quadratic formula. So like, what if there aren't any positive zeros? Then I'll have wasted time checking 4 of them. So when I get down to a quadratic, I'm just going to try to factor a quadratic formula. Well, this one factors pretty nicely. You have to have 2x and x. You have to have 1 and 1. Outsides would be 2x. Inside would be 1x. They would add to make negative 3x if they were both negatives. And then if you set those factors equal to 0, Here's our 1, and then add 1 and divide by 2. There's our 1/2. So I can add those to my list of zeros. 1 and 1/2. And check the original problem. It was degree 4, so we should have had 4 zeros, and now we have all 4. So we've got all the zeros. And then we want to write it as a product of linear factors. So that would look like f of x equals, and I'm just going to take each of these and put them back as factors. X plus 3, x minus 1. And you'll have to be careful with your fraction. To put x minus 1/2 would be incorrect, because then you would come up with a 1x to the 4th. Since you can see your leading coefficient is 2, we have to write that factor like when we factored the quadratic down below. It's going to be 2x minus 1. So if you could imagine multiplying all those first terms together, then you would get 2x to the 4th. Does anybody have any questions, concerns? Sometimes Descartes' rule of signs is amazing and helpful, and other times it might not give you that much information and it's all still like just guess and check. Okay, your homework assignment is 7 questions long. I'm going to pass back your quizzes from Friday, and if you want to do quiz corrections, those are also due tomorrow. So in addition to the 7 homework problems, you would be working on your quiz correction.